Hello, today I will be looking at a solver called bvp4c in MATLAB and Octave. What it does is it solves a system of ordinary differential equations like how we did with ODE 45. But if you remember, ODE 45 was for differential equations uh, which were which were time dependent. You had to define some initial conditions. But if we have to solve differential equations, ordinary differential equations, which are boundary value problems in which you have boundary conditions defined, then you need a different approach. And that is why we need a different solver, which is called bvp4c. Okay, so a type of problem that we can solve using this is the beam deflection problem, because that is a boundary value problem. It is boundary value problem because you define boundary conditions at the two ends of the beam, right? So first we need to figure out what the differential equation or the governing differential equation of the problem is. So let me look it up. Even I don't remember. I do, but I just need to confirm whether what I know is right or not. So the beam differential equation should give me the correct ODE. Beam, let's, or maybe I can search for the beam equation only. That will also return which is the equation I'm after. Yeah, so this is the equation which is this one. So this is the equation which defines which governs the deflection of a beam. The beam can be anything, simply supported, cantilever, any type of beam. All of them are defined by this particular differential equations. The only thing that changes within those types of beams are the boundary conditions. So let's write down this equation. It's d square by dx square ei d square w by dx square equals q. Okay, so q is probably a function of x. So, and another thing is, for example, initially we'll be considering simple problems. So in this particular governing equation, it assumes that E and I, which is the modulus, Young's modulus of elasticity, and I is the moment of inertia, it assumes that they are also functions of x. But we won't be looking at that for now. We want a simple enough problem, so we won't assume they are functions of x. So that will make them come out of the bracket. So I can write this as alright. So here Q is a load. For example, if I consider a simply supported beam, right, this is a simply supported beam. Q can be a uniformly distributed load on top of the beam. So this is Q of x, which is a constant here because it is same at all the points. E and I, you know, they are Young's modulus of elasticity and the moment of inertia. W is the deflection, right? So this is the governing equation that I need to solve, right? So yeah, the first thing that we do is all these ODE solvers in MATLAB or Octave, they solve a system of ordinary differential equations of the first order. So this is the fourth order equation. So I need to convert it into 4 first order equations. So the first one would be, let me call W, let me just name W as y1. So the first equation that we have is dy1 by dx, let's call that y2, dy2 by dx, let's call that y3, dy3 by dx, let's call that y4, right? I hope this is all making sense to you. And what would be the last one? The last one would be, if it all makes sense to you, the last one would be ei dy4 by dx q of x, or I can write that as this, right? So these are the 4 equations that we have sorry for this. So these are the 4 equations that we need to solve using bvp4c, because now we have a system of 4 first order ordinary differential equations. So now let's get back to Octave and start coding. Let me increase the font size. Okay, let me open up Octave. So bvp4c. So this so the people who will be running this on MATLAB, they probably don't need to worry about the next maybe 2-3 minutes of this video. For people who are running Octave, I need to instruct them on how to use the function bvp4c. So this function does not come bundled with Octave. You need to install it separately. So you know where we can look for packages, right? You can go Octave packages and I can get it from there. But the problem with bvp4c is it used to be a part of a package called ODE package, ODE-PKG, but that package is not currently supported, or it is not maintained by any individual, so it's been discontinued. So if you so these are the packages which are available, the ones with images and at the top, but inactive packages, right? So the function that we are after, it is part of an inactive package because it is not maintained anymore. So you can go to these links, any of these links, and you can get the source code, right? I clicked on this. So these are the inactive packages. I can install them from here. So this is the one I'm after, ODE-PKG. So you can go here, you can click on this download snapshot. Alright, so you have downloaded this. You can go to the downloads folder and see this is the one that you need. And how do you install it? So you type pkg install, then give the path to the place where your file is. Mine is at home folder. This tilde means home, downloads. If you expand this, so what I can do is I can either write home, it's the same thing, Divya Prakash, downloads, and this package, right? Yeah. So if I click enter, it will start installing this package. I have already installed it, so I don't need to do this anymore. If you don't, then you can follow these steps. Alright. So now what I need to do is, once I have this package installed, I need to, so I can check, if you want to check what packages you have, you can just type package list. So these are the ones which I have, general, IO, ODE, PKG, which I have already installed. So I can load that using pkg load ODE PKG. So now that package is loaded. If I type bvp4c, instead of telling me that this function is not defined, it tells me that there is an error. So probably I'm not using it correctly, but the function exists. Fine. So now we are on the same page, people using MATLAB as well as people using Octave. So let me start writing the code, right? So let me wait, I should have first navigated to the folder where I have my codes. Yeah, so let me write beam.m. That's, yeah, that looks good enough. So let's start writing the code. So before we do anything, we need to define certain values as in E and I. So E and I, they usually come together, so you can just write multiplication of both of them together, or you can specify them separately, or you can write them together. You multiply them away from this program. Anything will do. So I am just giving some made up values, so I'm just typing EI together, right? If you want, okay, no, let me keep it together itself. So EI is defined. Now you need to define the loading, which is a function of x, and let that load be some w value, right, or some constant value. Let that be 1. So this is the loading function. It is a constant, so whatever value of x you give, it will return c, which is 1. So this is done. Now I need to define the functions. So what I do is I just write a function called ODE1. This will be similar to what you did in ODE45. Let me check if it is recording. Yeah, it is. So I need to return four ordinary differential equations. The first one is y of 2, the second is y of 3, the third is y of 4, and the fourth is qx by ei. So q of x by ei. Alright, so these are the four functions, four ordinary differential equations that I have defined. Now I need to define the boundary conditions. So that is also specified as a function. So let me call this function boundary condition function, right? Or BC fun, yeah. This takes in two values because there are two ends, right? Two ends or two places where the boundary exists for a beam. So let me call those two ends as YA and YB, and let me return the boundary conditions. So I'll be solving a problem of simply supported beam. I do not remember what the boundary conditions for a simply supported beam are, so let me just look it up online. Those who are using these problems, they might have better idea. Boundary conditions. So let me go to this link. I guess this yeah, they should have it. Yeah, it does. Boundary conditions, cantilever beams. So I'll be doing simply supported beams, and these are the boundary conditions. So what it says is W of 0 is 0, W of L is 0. Okay, so what's W of L? W of what's W of 0? W of 0 is the deflection at 0. So in our case, the boundary conditions, yeah, in our case the boundary conditions are defined as YA here and YB at the other end. So if I have to define W is deflection. Remember, in our case it is YA, here it is W, and for us it is YA. So W of 0 is 0 means YA. Remember, you have to write in the same format as we did for the ODE function. So YA of 1 will correspond to your deflection, which is 0. So the way you write that is, you simply write here YA of 1. That's all. That is, you have specified the first boundary condition. What you need to do is, you need to actually, for example, let us say if it was YA of 1, for example, the deflection at one of the boundaries was 5, let's say, then you would write YA of 1 minus 5 equals 0, and then you input this in the boundary condition function. So there you would write YA of minus 1, 5. So that would be your specification of the boundary condition. But since it's equal to 0 here, you don't need to do that. So what's the second one? W of L is 0. W of L means deflection at the other end. So for us, that's YB. YB of 1 is 0. This was also 0, remember? So I can just write YB of 1. Next, it says double dash. So that corresponds, see, W corresponds to deflection, that's Y1. W double dash, single dash would correspond to Y2, double dash would correspond to Y3, right? So I can write this as Y, and it is defined at 0, so YA of 3, and lastly W double dash of L equal to 0, so YB of 3. And now I have defined all my boundary conditions. So if you do this once or twice, you will get to understand how this works. I also suggest that you look up the description of bvp4c in MATLAB website. They have more descriptive examples that will help you understand how this works. I'll be only solving a simple simply supported beam problem, which will give you a hang of how things work when you use these ODE solvers in MATLAB or Octave. Okay, so I think I have done these two. What else do we need? So so we also need to, we have four different things, right? We'll be getting four solutions, y1, y2, y3, y4. So what we need to do here in Octave is that, or MATLAB, is that I need to initialize the values of these solutions. So what you can do is, In MATLAB there is an easy way to do this. If you look it up, there is a function called bvp init, so you can do that, but that function doesn't work in Octave. So there is a workaround. What I do is I need to initialize. Remember, if you're solving for something, there are 4 unknowns that you will be getting out, so you would need some initial values for the function to start from. It will start from those initial values and eventually reach to the correct values. So before I initialize with the guesses, let me define the points where I want to initialize these values. So let me make a mesh. Mesh means the points where I want to solve for deflection. If the length of the beam is 1, let's say, my mesh points or my query points or mesh points, they go from 0 to the length of the beam in intervals of 0.1. Once you have that, you need to initialize these 4 unknowns. So what I do is I type y guess, and let me initialize it with ones for all these 4. So what I do is I create a matrix of 4 rows and 10 columns, 4 by 10, right? And why 10 columns? Because there's another way I can okay, let me say I want my values at 10 points. So what I do is I can create the mesh using some other method. So what I do, there's a function called linspace, which means linear space. So it generates points between 0 and L. And how many points does it generate? It generates n points. So n value is 10. So I get a mesh which has 10 points between 0 and L. This is another way to define an array of numbers between an interval. So now you have now you want to initialize your guess values for all the unknown y vectors. So you start with since you have 4 unknowns, y1, y2, y3, y4, you have 4 rows, and since you have 10 places or n places to fill up, you can specify this. So what this does is it generates a matrix of ones which has 4 rows and 10 columns. Okay, now what you need to do is you need to store these values in a struct. So in MATLAB or Octave, a struct is a data structure. So remember, I'll give you a very easy an easy explanation for this. Remember how you can look at these variables. If you want to store a single value, you just need to define a variable and store that number into that. But what if you want to store a lot of variables in a single package? For example, you can think of it as a school bag, right? You can keep your notebook, your pens, your textbooks, your lunch boxes in a single unit, right? So if you want to define a single unit where you can store, you can define something called a struct in Octave. The way you do that is simply you name your struct. So I name mine as sol init, which means solution initialization. So if I put dot x, it stores whatever value I input to this. So for example, my unit, my backpack, sol init dot x, so x is a compartment, you can think of that as a compartment. So sol unit, in the backpack sol unit, in the x compartment I store the x mesh. Again, in the same backpack, in the y compartment I store the y guess values. So let's see how this looks like. For example, if I now save and exit and open up Octave and run beam and look at what sol init is. It says it's a scalar structure containing the fields x and y. So within this backpack, within this single unit sol init, I have these values, right? 10 values of x and initial values for y1, y2, y3, y4. Okay, let's get back to my problem. Once I have this, I have all the components needed to solve or to use bvp4c. So what I do is solve, and I call bvp4c. The input it takes is the differential equations, again the boundary conditions, and the initial values, which is stored in this unit called sol init. And now let me run it. Okay, so I closed Octave, right? I did not, so when I open it again, I did not load the package. So every time this problem does not come up in MATLAB, but every time you open up an instance of Octave, you need to load the packages. So the package I need is ODE PKG and now it should work. So it says, okay, now I'm getting some error. It says y undefined. So let's look at what y undefined is. Okay, let me exit and just check what the error was. In which line was it? Line 8. Okay, alright. Okay, here I've written x and I have defined it in terms of y, so that's the mistake. So now I replaced x with y and probably this should work. Out of bound. Okay, another mistake. Y of 2, y of 3, y of 4. Why is it out of bound? Okay, I made another mistake. What I did was it's this function, these ODE, they are functions of x and y, right? So I cannot just write x, I cannot just write y, I need to write x as well. Again, and now the function is running. Again, this function does not take that much time to run in MATLAB, but since Octave is free, it is also slow. For learning purposes, that's alright. So yeah, let it run. Again, this hardly takes any time in MATLAB to run. Fine. Now I have the solution. And remember, the solution is also a struct. Solution is also a scalar structure containing the fields. So if you want to look at deflection, that's the first one, right? Y1. Okay. Solution has four. Okay, solution has something called sol.x, which is the value of the x locations, and it has sol.y, which is, it contains four. It contains a matrix which has 4 rows, and each row corresponds to y1, y2, y3 and y4 respectively. Y1 is our deflection. So let us plot the x values of the solution with respect to the y values, in which I only take the deflection values, which is there in the first row and all the columns. Let me plot that with a marker O and see how it looks like. Yeah, so this probably looks correct, I guess it does. How do I compare it? So what I do is I can search online for some ready-made solutions of these beam deflection problems. So let me search for some equations, beam deflection table. Yeah, that should give me. Yeah, let's go to this thing. Okay, so the problem I have solved for now is simply supported beam with uniform loading. This is the problem that I have solved. Simply supported uniform distributed load. Remember, these were the boundary conditions which I have input. They correspond to this particular case. So I can, I can compare the deflection which I have got using my ODE function bvp4c and the actual value of the deflection, which is given by this function. So here W is the loading. So don't get confused. Somewhere W is written as deflection, somewhere W is loading. We should know what we are using. So let me write down this equation. Let me edit beam and write down this equation. Deflection. It's a function of x and it is W by x. So for there it's W, for us it is C. And okay, we can do one more thing. Since the loading is downwards, it would be better that we specify this as minus C, right? Downwards negative. So anyway, it is Wx, so C times x divided by 24 divided by EI times L cube minus 2 times L times x square plus x cube. Okay, so this is the deflection function. Let's see whether we get the same solution. So let me plot a figure called figure 1. Let me plot the ODE value, bvp4c values first. So the deflection lies in y in the first row and all the columns. Let me plot it with O, and let me call, okay, this is something new. Let me call that line, the way I do that is I specify a display name. Let me call it bvp4c and hold on, because I want to plot another graph on top of it. Let me define some query points, or let me use the x values itself. So let me use sol.x, and now I want to evaluate my function, analytical function, which is given by def at these points. So I do def of sol.x, and I call this line, I give it the display name analytical, because that's the analytical solution, and let me run it. Again, it's going to take maybe a few seconds. I hope it's recording. It is. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, probably next time I'll just pause my recording so you don't have to wait. So now, okay, the first thing that you can see is the solutions are matching, but I gave them display name, but they did not show up. So I forgot to type this command at the end. I need to tell it show the legends, and now you can see that the circles correspond to the values generated by bvp4c, and the analytical solution is by the red line. Right. So now I have solved for a problem of simply supported beam with uniform loading using the bvp4c method. You can also check if your slopes are matching. So let me quickly do this. Let me also write a function for slope. That's also a function of x, right? And it is let me just copy this. Excuse me, it's y. Okay, I just need to make some changes to this. This is what, just open it side by side. This is w, which is c times x divided by 24 ei, same thing. L cube minus 6, okay, this is L cube minus 6 lx square plus 4x cube. Okay, so now I have the slope. So what I can do is I can, let me just copy all these things. All right, so how many lines? y4, y will copy, okay, y4, okay. So now what I need is, I need to name this figure 2. Let me also type legend show, which I forgot. Okay, so this is, see, remember the first row has the slope values, the second row has the, the first row has the deflection values, the second row has the slope values. I can also give it a title, right? Let me call the title as deflection. That's the title of the first one. The title of the second one is again legend show, and title slope. What else do I need to change? Yeah, instead of depth, now I'll be calling slope at all the x points. And let me just run it quickly. Okay, so I made an error. I forgot to specify the multiplication sign, the asterisk. So this is running again. It'll take 10 seconds. So let me pause it, because we don't have to wait. Let's just wait, because this is anyway the last part of the problem which I'll be doing. So again, the same code will work in MATLAB. You don't need to make any changes, but it is quite simpler to execute in MATLAB in terms that it is much faster, and you can okay, so the solution is not matching. Let me check why that's the problem here. Let me just go back. Let me check if I have written the equation correctly. Yeah, it is slope is minus c times, okay, it was L, this x isn't there, so that's the mistake I made. So that's why it's not matching. See, there's no x here. It's minus w by 24ei minus c by 24ei, L cube minus 6 lx square plus 4x cube. So this should work. Let me pause it so you don't have to wait. Okay, so this the code ran, and this is the plot that was generated for this one for slope and this one for deflection, and as you can see both these values match, so we are able to do this correctly. So as I told you, I was telling you earlier, this same thing will work in MATLAB, and you can look at the documentation of MATLAB for understanding this function bvp4c in more detail. And you can also plot the bending moment, the shear force, because the third row, if you remember, y3, it corresponds to the bending moment. So this third row divided by ei corresponds to the bending moment, and the fourth row of the solution, or y4 divided by ei, corresponds to the shear force. So you can draw bending moment diagram and shear force diagram using y3 and y4. Alright, so I think this is enough. I hope you'll make use of this bvp4c function in your beam deflection problems. So remember, the only thing that changes for different types of beam problems is the boundary condition. For cantilever beam, for example, if you look here, for cantilever beam, the only thing you would need to change is the BCFCN function, FUN function, and you would need to input these boundary conditions, right? That's the only thing that will change in the code. The only thing that will change is this function. Everything else remains the same. So I hope it was that you learned something, and I'll probably see you in the next video on Octave and its tools. So thank you for watching. Bye.